All right. Where's my answer? Between combination and permutation? If you could just remember that permutation, order matters, combination, order doesn't matter. I don't say that example again. Are you placing them in order? Like one has to be the best restaurant, the second best restaurant. That order doesn't matter. That's combination. Oh, you're right. So it is permutation. Wait, no. But you're just trying to find the probability of selecting four of them. So like if you have like if we go back to that we did an example where it was like the hospital or whatever, where you had to go to like 6 different patients. Yeah. So like if you had 6 patients, but then on part B it said like if the nurse must choose 4 to visit. Oh, I see. Yeah. Because no, it is a permutation. Yeah, but yeah, because that one is permutation because the issue is yeah, if you do go to that house first, you can't go to it second, third, or fourth. Hmm. Yeah. But then if you go to the example 24 with the combination, we're just trying to set up people in a group. That's not going to matter because they're still in that group. But I guess if you're going to different places or going to a different restaurant, if you go to that restaurant, yeah, you can't use it again. Yeah. Yeah. I can see how that could get confusing. Yeah, because I think we were doing an example last night where it was like a mutually exclusive. It was like a phone call and text messaging. And you're like, how is that? Is that? And I think you said it was not mutually exclusive because you can actually make a phone call and text at the same time. Yeah. So, and I was like, that's a 21st century question right there because that's a horrible example. All right, so let's look at this right here. I need to write down the information. What would we start with? 16 women, 12 men. 16 men, 12 women. We're just gonna assume. All right. All right. So on part B, it says find the probability that no women are selected to work on the shift. All right. So what's nice is on the bottom, the amount of orders you can get is the same as last time. And we finished that off by saying this was a combination because the order didn't matter as you're selecting 8 people for this shift. And the number came out to 3,108,105. We were talking about maybe doing 28 or yeah, 28 to the 8th power. That's false because if you take one out, you have to get rid of them. So it'd be like 28, 27, 26, 25. But then the combination. So then you have to then divide that by the 20 factorial times the 8 factorial. All right. Anyway, so that was the number that we got yesterday at the conclusion of the class. That is just your total amount of options to choose 8 people out of 28 people. But now we want them to not be women at all. So this time I just want the combination because it doesn't matter the order of men. It just can't be women. So to do that, we need to figure out the combination of picking men out of 28 people. So what's my N? 28. And then what's my R? Right? Oh, oh, I got that backwards. So this is 16 women and then 12 men. Okay. Men. No, I didn't know because I don't see it on my page anymore. All right. So, and then how many, well, I guess really and truly, I don't have 28 total because I'm selecting how many people from. I don't have 28 men. I have 12 men. Because I want it to be a man. I don't want no women in my A group. Nope. Because how many people are we selecting though? 8. That was on part B. Part B, I wanted exactly 3 women. Part B, I don't want no women. Yeah, this is a whole new question. So on this one, I have 12 men and I want to choose 8 of them. Right. So I don't have any women. And to do that, we then do its combination thing. So that would be 12 factorial over 12 minus 8 factorial times 8 factorial. Right. And again, that should be 12 factorial. And then 4 factorial times 8 factorial, making sure those add up to 12. You would now get 12 times 11 times 10 times 9. This 8 factorial will cancel out the rest. Divided by 4 times 3 times 2. Anything else I can reduce? 4 times 3 is 12. 12 goes away. Anything else? 2 goes into 10 5 times. So now I get 11 times 5 times 9. I feel like we've done this before. Yeah, what's 55 times 9? 490? 495. I feel like that number looks familiar. Yeah, there it is. Make sure we got 495. I was looking at 792, but that was yesterday's. All right, so 495, and then that's it. And then the total is still this amount of combinations. So then you would type this into the calculator. Everyone know that decimal conversion? That one's the one we got memorized, right? I don't know. 495 divided by 3108105. Yep, so this would be, I need that back. So this would be equal to 123,159. So that's times 10 to some power. So if it's a negative number, you move the decimal to the left that many. If it's a positive number, you move the decimal to the right that many. So if I move the decimal to the left, there's already one number there. Therefore, there's only 3 more zeros that are needed. Yes, that's why I made it 0.00159. So in this case, you basically have a 0.02% of getting an all man shift out of 8. That's kind of crazy. Any questions on B? Oh, see this E? So if it's a negative number, you move the decimal to the left. Yeah, after at the end. The E right here represents times 10. So if it's a negative, you move to the left. If that number is positive, you go to the right. Yeah, so that's 4 places to the left. So since 1 represents 1 place, I just need 3 more placeholders as zeros. Like this number? Oh, I just if it's a -4. Had this been like -7, I'm gonna put 6 zeros. Yeah, this tells you just how many decimals you're gonna move to the left. All right. Any other good questions like that? All right. Let's look at part C. Grant, all of these answers are already in your book. I just wanted to work it out with you. All right, so let me see if I can write these numbers down correctly this time. How many men were there? 12? 12 men, 16 women. All right, so now I want to find the probability that all the people selected to work the shift are women. All right, so the bottom number still won't change. So that's going to be the 3,108,105. All right, and then I need to find all of them are going to be women. This time I have 16 women, and I want each one to be a woman. So what's my N going to be? 16, and what's my R going to be? 8, because I'm selecting 8 people for this shift. So that's going to be 16 factorial. I don't know. I doubt it because there's more women to choose from. It's more rare to have more men because there's. Oh, you talking about like the people in the group being chosen? Yeah. This will be more because we have more women. All right, so this right here is 16 minus 8 factorial times 8 factorial. Again, if you skip some of these steps, totally okay with that. 8 factorial times 8 factorial. So this will now leave me with 16, 15, 14, 13, 12, 11, 10, 9. All divided by 8 times 7 times 6 times 5 times 4 times 3 times 2. Anything I can cancel? 2 and 8 make 16. Anything else? 3, 5 make 15. Anything else? Six goes into 12 2 times, so that's another 2. And then those both make a 4, right? So I'll just cancel that ultimately and get rid of that 4. So I really just have 13 times 11 times 10 times 9. Anybody know what that is? Go ahead. So we made those both 2s, and then 2 times 2 is 4, so I was able to delete that last 4. 343 times 9, that's 7. Yeah, 2,937. 2,939 or 37. And when I said that, I really meant. I don't think it's any of those numbers. Hold on. 13 times 11 times 10 times 9. I really said 12,870. Yes. Yeah. I think that's what you said too. So that's our total options there on making a full women's staff out of all the options I had. We simply just plug that into the calculator. We can definitely tell the odds are going to be much higher. So 12,870 divided by 3,108,105. No E in this one, so that's going to be straight up. Yeah, that's what I'm going to go with. So in this case, we actually have a 0.4% chance of selecting an all women's 8-person staff. So. Yeah. Well, really, those are still pretty low statistics for both. All right. Part D now says find the probability that at least one woman is selected to work the shift. So this is where that C word, the compound, huh? I think it's compound. Let me go find it. No, it's not compound. Complement. So if we do the complement in this situation, it's a lot easier because if we figure out the probability of at least one woman, you would have to go find the probability of there being exactly one, probability of exactly two, the probability of exactly three, exactly four, exactly five, exactly six, exactly seven, exactly eight. Add all of those numbers up, but that as your numerator divided by the 3 million number, which is your total options. That is a lot of work. That's 8 processes we're going to figure out. It'd be a lot easier just to figure out what's the probability of not getting a woman at all, which is the complement of at least one woman. So if I just find the complement of this, that would be 1 minus no women, which is great because we just did that, right, on part C. So the probability here is now just going to be 1 minus 0.0041. And so number 1 was D, not C. Oh, sorry. Part B. Yep. Let me go back. Let me erase. The no women was what? 5.9. All right. So there's your no women. Huh? 159? 00159. We have the right number now? All right. So if I find the probability of no women, which I've already done on part B, not C, I can then, that will basically be the number that's left of the probability of exactly 1, 2, 3, 4, 5, 6, 7, 8 women, which is what would at least one woman be. So in this case, the probability of at least one woman being selected becomes a 1 minus 0.000159. And you have a 0.9998 probability, which is a 99.98% chance of at least one woman being selected in this group. I just went to 4. It felt good. I don't know. I didn't want to round. So that's kept on writing the numbers until the next number told me not to round. It's kind of how I've been doing it in my head. Unless it tells me what to do. I mean, I really don't know. 4 is always a good option when you're doing probabilities to percent. Any questions then? On the next page, they have all of the work that we just did together. So let's look at example 27. So maybe we can do a problem they did not work. So these type of problems are going to take a lot of practice. So make sure you're practicing these. All right. So on this one here, it says a sequence of home colors. There are 5 houses on a cul-de-sac in a deed restricted neighborhood. Oh, my bad. In a deed restricted neighborhood, not dead. That would suck. All right. It is time for all the houses to be painted. The homeowner association has approved 3 colors of paint: beige, blue, and yellow. I never really liked deed restriction in neighborhoods because I feel like I don't own my stuff because I still have to ask permission to do stuff to it. Yeah. There you go. No access roads. I like it. They could travel wherever they want. And I think they have the authority to cut it down too. All right. So first option says, how many different color sequences might be chosen to paint the houses? So we had 5 and they get 3 each. So what would I do to figure that out? Not 5 times 5 times 5. There it is right there. Each house, go ahead. I don't think so. I think they only get to choose one singular color. No trim even. I think even the roof has to be the same color. Yeah, everyone's got to have the same cookie color things. All right. All right. Anyway, so each house has 3 options. So there's 5 houses, right? Yeah, 5 houses. So that means the first house has 3 options. The second house has 3 options. The third house has 3 options. The fourth house has 3 options. And the fifth house has 3 options, also known as 3 to the 5th power. And now that doesn't tell you how many different color schemes you can get here. Yeah, there you go. Perfect. Way to go, Charlie. Yeah, 243. Any questions on how to find all the total combinations there? All right, part B then says, what's the probability that all 5 houses would randomly select the same color? All right, so that it doesn't matter which one they choose, but if they choose the same color, we have to find out how many options they have there. Yeah, I guess so, because they have, because you could basically, what's that? No, because so does order matter here? No, it's random. So basically, let's see. They have 3 options. They're only going to choose one. So I feel like our N would be 3 and our R would be 1. Yeah, I think so. Yeah, because this right here then ends up being 3 factorial. You're right. Because it ends up being 3 minus 1 factorial times 1 factorial, which is, and I don't really need 1. And then now just left with, yeah, you're right, just 3. They only have 3 options. We could have just looked at what we had here. Yeah. I don't know why I felt like using the formula. How's it? Okay, so basically what happens is the 1 goes away because that's just 1 factorial, but this is 3 times 2 times 1, and then 2 times 1. So you just get 3. Well, so that 3 is not the answer. Sorry. 3 is just the probability that they all select the same house. So out of all the 243 cases, there's only 3 of them in which they would all select the same color. So either they're all going to be blue, they're all going to be yellow, or they're all going to be beige. There's your 3 options. So whatever that probability is. That wasn't a very good answer. Let's try that again. That's better. So that would be 0.0123. 5. Oh, look at that. Oh man, if there would have been an 8 there, that would have been a cool number. Ooh. I bet this is a famous fraction or something. All right, so there you go. So you basically have a 1% chance that they'll all select the same color house. Any questions on that one? So yeah, I definitely went too far in detail on that one because obviously there's only 3 of them that could be it. Yes, go ahead. You wouldn't go to 0 though. You stop at 9. So yeah. Yeah, because the repeating decimal already started. So it'd be 4, 5, 6, 7, 9. Then the 0 would start the pattern again. If you want to do that, I wouldn't count it wrong. But I think it looks cleaner with 4 decimals. All right. Any other questions though? All right, cool. That was a lot easier than the one we just did. What is next? All right, looks like example 28, decorating colors. So a decorator is selecting colors for the den walls, the sofa, and the accent chair. when does chair start having accents? Like it's like a Texan accent or like a European accent or yeah. I don't even hear the accent of my chair. Whatever. What accent? How do you say the word? I can't. I don't know. I don't know. Words are hard. That's fine. It's whatever. All right. So she can choose from 10 colors for the wall, 5 colors for the sofa, and 3 colors for the chair that has a country accent. Is that how you say it? You know, those two C's should just be. All right. All right. Anyway, so first part says, how many ways can she choose the colors? So remember, this is the counting rules thing where all you got to do is just multiply each of your options here. So this will just be 10 times 5 times 3. And what does that give you? That's 50 times 3, which is in fact 150. Yep. Part B says, what's the probability that if colors are randomly selected, she chooses seafoam green, sofa, and a turquoise chair? You're not my decorator. All right, so we gotta have a probability that only one color is chosen here, one color is chosen here, and one color is chosen here. So but this is a combination, or is this a permutation? Ooh. Order does matter because if I choose the color, I can't choose it again. Oh, I see what you're saying. So if we just pay attention to that, yeah, so this will just be 1 out of 10 then of choosing this one, and then 1 out of 5 on this one, and then 1 out of 3 on this one, and then still using the counting rule, we can just multiply those 3 together. So then that'll just give us 1 out of 150. Yeah, I don't see why that wouldn't work. I don't know why. How's this attached to a combination and permutation when these questions like don't use them? That would be it. Yeah, no, that's the answer is 1 over 150. Because I mean, you only have 1 out of 10 options on the seafoam green, 1 out of 5 options on the yellow sofa, and 1 out of 3 options on the turquoise. According to the counting rule, you just multiply all your options together. It's basically this and this. Well, that and there means what to us? Multiplication. So that's all we do. Oh, just trying to figure out what's left. Oh, like if you're all 3, maybe we'll have time at the end of this to look at that. All right, and that's pretty much it on 28. Just 0.006% chance that there's actually it's a 0.7% chance that she'll have all these ugly colors. I don't even know what seafoam green is. All right, this is we had a few more. Okay. So example 29, it says selecting seminar attendees. So in a company with 9 executives, of which 4 are women and 5 are men, 3 are selected to attend a management seminar. Does order matter? No, because they're going to this seminar, but it doesn't matter if you're selected first, second, or third, you're still going to the seminar, right? So find the probability that all 3 selected will be women. So first, let's find all of our combinations. So we have in a company 9. Yes, I have 9 executives, 4 women, 5 men. 3 are selected to be my president, vice president, and secretary. So now if I select Charlie to be my president, he cannot be vice president and secretary. But here I'm just selecting 3 people to go to a seminar. It doesn't matter if I choose you first or if I choose you third, you're still going to the same seminar. Oh, I'm not saying your probability changes from being selected. You go higher up by being selected, but it doesn't matter where you were selected at because you're still going to the same place. Yeah, so like the restaurant thing and the hospital thing, if I go to this building, I cannot physically go to that building again if I go check this next thing or go eat at this next restaurant, whatever that other example was. Yeah, like if it's ordinal, right? If it's ordinal data, then it has to be it has an order to it. That means order matters. But if it's just like not ordinal, basically, it's permutation. Yeah, it's combination. Mm-hmm. All right, so yeah, so to find out all the stuff, our N is going to be 9 and our R is going to be 3. So this becomes 9 factorial. Since we determined that the order does not matter, this would then be 9 minus 3 factorial times 3 factorial, which then just gives me 6 factorial times 3 factorial, which is just 9 times 8 times 7, 3 times 2. You think I can cancel? Okay, so I really just have 3 times 4 times 12. So, oh, that's not 12, 7. 3 times 4 is 12. 12 times 7 is what, 84? Go ahead. Well, I'm just saying like 7 times 11 is 77. That is at 7 more and got 84. The 7 times 2 and got 4, and then 7 times 1 got 7, then add it. I don't even know. Sorry, that's not even a question. I don't know where your math went there. Why'd you get to 160? Anyways, no, this isn't even a question. This is just our bottom of our fraction. This is our total amount of options we have. Now we can go over here and figure out, all right, what's the probability that all 3 women are selected? So now I want the probability where my N is 4 and my R is 3 because I want all 3 women to be selected. So this now becomes and it doesn't matter the order still. So this would be 4 factorial. Then 4 minus 3 factorial times 3 factorial. So that would give me 4 factorial over 1 factorial times 3 factorial, which is really just 4. Yep. So then the answer here tells me this is 4 over 84, which is 1 over 21, which is a 0.0476. So a 4.7% chance that all of them will be women. Where? Right here? 1 over 21, yeah. 4 over 84 simplifies down to 1 over 21. That makes sense? Hmm? The next one's like all three need to be min this time. So now my n is, what's my min? 5. So my n is 5. I'm still only selecting 3 of them. So now I get 5 factorial over 5 minus 3 factorial times 3 factorial. So I get 5 factorial over 2 factorial times 3 factorial. So then I get 5 times 4 over 2, which is just 5 times 2, which is 10. Y'all agree? Any disagreements? Then that just becomes 10 over 84. You can simplify if you like, but I'm gonna go straight to the calculator. So this is 0.1190. So that means that if I wanted all men to go, I have a 11.9% chance that that will happen. Any question on that probability? 1190. Part C then says find the probability that at least one of the people selected will be men. So it's a lot easier to figure out what's the probability that none of them will be men. Now we haven't done that, so we're gonna have to do that work here. So again, if we didn't do the complement here and we went through this process that at least one would be a man, I have to find out how much exactly one man gets chosen, how much exactly 2 men get chosen, find out the probability that 3 men get chosen, add those results up, and then divide that by the 84. None being chosen, and subtract that from 1. No, that'd be, I don't think that's going to be the same. It might be. You know what? Maybe. Let's think about that. If I know I don't want no men, then I then only have the 4 women and 3 of them are selected. That is, you're right. And because if no men are selected, then that means all 3 of them are what? Women. So we have done the work. So if we do that as 1 minus no man selected, where's that at? 0.046. Then I'll find out where at least 1 man will get selected. That's perfect, man. I was about to do this a lot harder. Way to think, guys. 0.0. So in this situation, the probability that at least 1 man gets selected is a 95% chance that at least 1 will be going to this seminar. Questions on that? All right. Now on the next one, it then says find the probability that 2 men and 1 woman will be selected. So what you got to do is you got to find the probability of 2 men being selected. And means what? Multiply. Let me make sure I'm good. Oh, because you do that same thing with the women, right? Well, no, because now you don't want at least 1 woman. You just want 1 woman. Do that. Let's see. The process I was doing in my head was if I need exactly 2 men to be chosen, this would be, yeah, men's 2. So my man one here, I would say my N is 5, my R is 2. So this will give me 5 factorial over 3 factorial times 2 factorial. Do y'all need to see me subtract there? Okay. Multiply by 1/3. Oh yeah, yeah. That's what we're looking for is the probability. Right now we're just trying to find the total options here. Here I got what's this gonna be 5 times 4 divided by 2. So that's 20 divided by 2. That's 10 options. All right, so men have 10. Now we got 40. We got Oh, that is. It has the same odds, I guess, of getting exactly 3 men or 2 men. That's not always going to be the same, but that's pretty cool that that did work out like that. All right, now let's do the women part. So this now would be n is 4. I want 1 woman. So now I get 4 factorial over 3 factorial times 1 factorial, which is just 4. Is that the same here too? What is the odds? Now I want to know if that always works. I don't know. I just got the number. So this will be 10 times 4 because and means to multiply. And I have 84 options. So this now gives me 40 out of 84. So that would just be 40 divided by 84. And that would give me 0.476. No, you only have 84 chances still or options. Oh, sorry, I thought I took a step back. History. So I did 40 divided. That answers for part C. Part C was at least 1 person is a man. Yeah, but we just did D. He just got the same answer for C. I don't know. Yeah. I just think it's cool that we got the exact same numbers. And now I'm wondering if that's always going to be the case. I don't know. Let's look at the next one. Try your theory, Ella, and see if you get it. And I'll go the same process here. So this one's now 2 women. So 2 women would just be 4, 2, 2. To get 2 women, that would be 4 times 3 divided by 2. So is that I got 6 that time. It was a good theory. I don't know. We just got 6, so I didn't get 4 again. Because if I want exactly 2 women, I have 6 options. We'll have out of that's good. Yeah, 6 of those options will be 2 women, and then 1 man. Didn't I do 1 man already? Oh, I'll do it again. No, I did do 1 man. Where's 1 man? Oh, but I don't need that number. I need the top number so I can do the. I'll just have to do the math. Man is 5 factorial over 4 factorial, 1 factorial. Yeah, so it's just 5. Yeah, so the numbers didn't be, that wasn't the same. I was curious though. So then I would just do 6 times 5, which is 30 over 84. And that would give me, I don't want the history no more. All right, so that's 0.3571. So we have a 35% chance of selecting 2 women and 1 man. Fun statistics. You look really into it still. All right, so let's do a few more to make sure we really got this stuff down. I want to see nothing but hundreds. Remember, you do have 2 homeworks this week. All right, so on this one, it is the lottery numbers. So in a lottery game, one selects a 3-digit number with repetition of digits per minute. What is the probability that all the digits are the same when the winning number is selected? So we're looking for a probability, or how many? Yeah, what is the probability? All right, so we need to find out the total amount of options we have. So it said what again? So it says in a lottery game, one selects 3-digit number with repetition of digits. All right, so how many digits are there? 10. Very good. So there are 10 digits. And then how many of those 10 digits am I selecting? 3. There's only 10 digits you can make up a number with, 0 through 9. So that's just the stuff that I guess they're just making you assume. And I want 3 of those digits. Now, it does say with repetition. So is that going to be permutation or combination? Combination, because order is not going to matter because I can keep on repeating. That's not this is not a combination or permutation situation. This is the counting rule situation. You just multiply, because how many options do you have for the first number? 10. What do you have options for this? 10 times 10 times 10. Yeah. So all of the, so that's not the answer there. That's just the bottom number. All of the digits are the same when the winning number is selected. So like that means like all zeros, all ones, all blah blah and stuff like that. So we can actually just think about that. All of them are 0. All of them are 1s, 2s, 3s, 4s, 5s, 6, 7, 8s, 9. How many options do we have? 10. So we can just say this is just 10 out of 1,000, which is 1 out of 100, which is 0.01, which is 1% chance that all 3 numbers will be selected the same. Yeah, randomly, yeah. You have 1 out of 1,000 for a pick 3. Well, yeah, that's what he was talking about. You don't know them, but if whatever their 3 digits is, there's only one of those that's his favorite, and then so 1 out of 1,000. So there's a 0.1% then chance then of winning. It is going to be a fun one. All right, so I think we got one more, and then we're done. All right, let's do it. Let's finish it up. So this is gift basket contents. All right, so the gift basket department at a local upscale grocery store has pre-made gift baskets containing the following combinations in stock: coffee, tea, cookies, mugs, candy. All right, how many options are there? EF. Okay, I'm just gonna do it like this, where I have F in the screen. Let me go to the table. Here's the table. All right, so let's look at this. So if one basket is chosen at random, it contains coffee or candy. Well, first of all, you got to figure out the total of items. So how many is there? So we got 20 plus 12, which is 32. 32, 42, 55, 65, 77. All right. Okay, so 77 is going to be our bottom number. That's our total options. In one basket, it's chosen at random. It contains coffee or candy. Or means what to us? Add. Because I can't put it up there. Hold on. Let me scroll up for a second. So you can write this down, then I can come back down. All right, so clear. This is how you read these type of tables. You have a total of 77 of these items. Out of these 77 items, 20 plus 13 is 33. You have 43 that will have coffee. 12, 22, 34 of them will have tea, also equals 77. Out of those options, 32 have cookies, 23 have mugs, and 22 of them have candy in it. And that also totals up to 77. Right. That's how this is read. Everyone get that written down? Okay. I'm gonna scroll back to the question. I guess it's right there. Hold on, I'll keep it here. All right, so again, we have 77 as our total. Or means to add. So we got 77 right there. So coffee, 43. There's 43 of them that have coffee. Candy is 22. Because they're not mutually exclusive, right? So then I need to subtract what has coffee and candy. So subtract 10. Okay, yeah. So that'd be 10 out of 77. That's perfect. Now remember, you don't do anything with these denominators. So 77 is just going to be the remaining, the bottom number. 43 plus 22 is 65. 65 minus 10. So you have a 55 out of 77 odds. If you divide that by 11, you have 5 out of 7. So that's 0.71. So you have a 71% chance that you'll get coffee or candy in your basket. That's pretty good odds if you like coffee or candy. Same process on this next one. If one basket is chosen at random, it contains tea, given it contains mugs. So this part right here, we talked about this previous section. If it's given, that means that already happened. So I have to assume that it's going to contain mugs. How many contain mugs? So that's your bottom number now. Now that I know it's got mugs, how many of it has tea? 10. So you have a 10 out of 23 getting a gift basket, given that it has a mug in it. All right, just for sake of time, it's just 0.43% or 43%. All right, if one basket is chosen at random, it contains tea and cookies. Now, typically that means multiplication, but with this chart, we can just look at it. So tea and cookies is what? 12. And how many total are there? Whatever that number is. Not understanding the chart? So these are all your totals. I don't know what that point of view looks like. Everything looks like math. Oh, it comes with coffee and cookie. Each gift bag has 2 items in it, basically. This comes with coffee and a chocolate chip cookie. This is tea and a chocolate chip cookie. And then this is a coffee and then a coffee or maybe a juice mug. I don't know. And same process there. All right, and then it kind of just keeps going from there. D, 3 baskets are chosen at random, not replaced. All the baskets contain mugs, so they're not replaced. So if they contain mugs, that's going to be 23 out of 77, 22 out of 76, 21 out of 75. Find out whatever that probability is. E says if 3 baskets are chosen at random and not replaced, none contain mugs. Well, 23 of them. Subtract that from 77. This is part E. What's 77 minus 23? 77 minus 23. 54. Okay, so that's going to be 54 out of 77, 53 out of 76, and then what was it, 3 baskets? So then 52 out of 75, whatever that is. And then the last part, if 3 baskets are chosen at random and not replaced, at least one contains mugs. Didn't we just do that? Oh, it does. Wait, what? Oh, this one says at least one. So you would have to find the probability that none are going to be baskets and then subtract that. So this was, E was no mugs, right? So whatever that probability is, you'll do 1 minus E. And you'll at least get 1 mug. Whatever you get for E. And that's it. That's all I got. Feel free to leave.
All right.